Welcome to the Antonio podcast that discusses a variety of scientific topics. Nuclear craters and Carolina bays. This video discusses the nuclear craters in the Nevada test site and the derivation of yield equations relating energy to crater size used today to estimate the sizes of meteorites that impact the planets and moons of our solar system. The glacier ice impact hypothesis proposes that the Carolina bays were created by secondary impacts of glacier ice ejected by an extraterrestrial impact on the Laurentide ice sheet during the Ice Age. The oblique impacts by the glacier ice boulders created inclined conical cavities that transformed into shallow elliptical bays by viscous relaxation. The energy of the glacier ice impacts can be calculated using yield equations that correlate impact energy to crater size. In 1989, Professor J. Milosh published the book Impact Cratering, a Geologic Process. The book contained formulas relating impact energy to crater size. Professor Milosh's formulas were adapted by Ross Bayer for an online program that computes projectile size from crater diameter. The calculator takes into consideration the velocity of the projectile, its density, the impact angle, and the target characteristics. This calculator can be adapted for use on the Carolina bays. The program to calculate projectile size from crater diameter assumes that the crater is circular. By equating the area of a circle to the area of an ellipse, we find that the equivalent radius of the ellipse is the square root of the product of the semi-major and semi-minor axis. The diameter of the ellipse can then be used to calculate the projectile size. At this time, this is the best way of adapting the yield equations for the Carolina bays. On January 11, 1951, the United States Department of Energy established an area for testing nuclear devices in Nevada, 65 miles northwest of the city of Las Vegas. It was originally called the Nevada Proving Grounds. A November 1951 nuclear test with a yield of 21 kilotons of TNT was the first U.S. nuclear field exercise conducted with live troops maneuvering on land. The troops in this image were located 6 miles away from the blast. Today, the area is covered with hundreds of craters made by nuclear explosions. The Nevada test area covers approximately 1,360 square miles of desert and mountainous terrain. The first test began with a 1-kiloton bomb dropped on January 27, 1951. Las Vegas experienced noticeable seismic effects. The mushroom clouds could be seen from the downtown hotels, and the nuclear tests became tourist attractions. The Sedan crater was excavated by a nuclear bomb on July 6, 1962. The radioactive fallout from this test contaminated more U.S. residents than any other nuclear test. The bomb that made this crater was a thermonuclear device with a fission yield of about 30% and a fusion yield of about 70%. The bomb itself had a diameter of 17 inches, a length of 38 inches, and a weight of 468 pounds. This was approximately the size of a 55-gallon drum designed to fit inside the warhead of a Minuteman intercontinental ballistic missile. The Sedan explosive device was lowered into a shaft drilled into the desert alluvium 194 meters or 636 feet deep. The blast had a yield equivalent to 104 kilotons of TNT and lifted the dome of Earth 90 meters or 300 feet above the desert floor before it vented at 3 seconds after detonation. The blast exploded upward and outward, displacing more than 11 million tons of soil. A circular area of the desert floor 5 miles across was obscured by fast-expanding dust clouds moving out horizontally from the blast site like a pyroclastic surge. The resulting Sedan crater is 100 meters or 330 feet deep with a diameter of about 390 meters or 1,280 feet. The blast caused seismic waves equivalent to an earthquake of 4.75 magnitude on the Richter scale. The radiation level on the crater rim at 1 hour after burst was 500 roentgens per hour, but it dropped to 500 milliroentgens per hour after 27 days. The crater is visited by over 10,000 people per year through the free monthly tours offered by the U.S. Department of Energy. Overall, 928 tests were conducted in Nevada, and there were 1,021 detonations because some tests involved more than one device. The radioactive cloud from the Sedan explosion separated into two plumes, rising to 3.0 kilometers and 4.9 kilometers. That is 10,000 feet and 16,000 feet. The two plumes headed northeast and east toward the Atlantic Ocean. Nuclear fallout dropped along the way as the radioactive clouds drifted over the United States. High levels of radioactivity were detected in Iowa, Nebraska, South Dakota, and Illinois. It has been estimated that the radioactive doses were large enough to produce 25,000 to 50,000 cases of thyroid cancer around the country, of which 2,500 would be expected to be fatal. The book by Professor Meloche explains how the equations correlating impact energy with crater size were developed. Military pressures of World War II brought explosion craters under scientific scrutiny. Subsequent concern over the effects of nuclear weapons fueled a large and continuing effort to understand the physics of explosion cratering. High-velocity impacts attracted interest because of the anticipated meteoroid hazard to vehicles flying in space. In the chapter entitled Scaling of Crater Dimensions, Professor Meloche notes that one of the most frequently asked questions about an impact crater is, how big was the meteorite that made the crater? Like many simple questions, this has no simple answer. It should be obvious that the crater size depends upon both the meteorite's size, speed, and the angle at which it struck. It also depends upon factors such as the meteorite's composition, the material and structure of the surface in which the crater forms, and the surface gravity of the target planet. The scaling laws were first introduced in 1950 by C.W. Lampson, who studied the results of a series of TNT explosions using charges ranging from 4 to 1,500 kilograms. Lampson's work was originally commissioned by the National Defense Research Committee at Princeton, New Jersey. Lampson noted that parameters describing different size explosions could be expressed by similar equations if all the distances, such as depth and diameter, were divided by the cube root of the explosive energy or yield. The ratio between crater diameter and the cube root of the energy was found to be nearly constant, independent of the energy. Crater diameter is thus proportional to the cube root of the energy. The relationship between the crater diameter and the cube root of the explosive energy permits extrapolation of experimental results on small craters to predict the size of craters produced by larger explosions as shown by this equation. The results can be generalized for different types of target materials so that it is possible to deduce the depth, volume, and diameter of a crater from the energy of the explosion. The table in this image shows the experimental power law scaling constants for various target materials. These constants are integrated in the Meloche-Bayer program that calculates projectile size from crater diameter. This graph shows the scaled crater diameter versus the scaled depth of burial. From this graph, it is possible to determine how deep to bury an explosive to get the maximum crater size. The impact of a meteorite would correspond to an explosion at the target surface with a burial depth close to 0. The nuclear tests that were conducted at different depths are highlighted in red. When a nuclear device is buried at sufficient depth, the explosion may be contained with no release of radioactive material to the atmosphere. The United States conducted 210 atmospheric nuclear tests between 1945 and 1962, with multiple cameras capturing each event at around 2,400 frames per second. The Lawrence Livermore National Laboratory has declassified 497 of these videos and placed them on YouTube. Operation Hardtack was a series of 35 nuclear tests conducted by the United States from April 28 to August 18 in 1958 at the Pacific Proving Grounds. The tests were designed to identify the radiological exclusion area and safe zones for ship positions and aircraft participation. This film shows the detonation of a 25-kiloton nuclear bomb on a barge in the Bikini Atoll. Louis Riard, a French fashion designer, introduced a two-piece swimsuit, which he called the Bikini, 4 days after the first test of an American nuclear weapon at the Bikini Atoll, which is part of the Marshall Islands in the middle of the Pacific Ocean. Nuclear testing began in 1946 after the residents were evacuated. 67 tests were conducted, many of which produced significant fallout in the region. The testing concluded in 1958. The inhabitants who were evacuated are still waiting for the $2 billion in compensation assessed by the Nuclear Claims Tribunal. The islanders and their descendants live in exile because the islands remain contaminated with high levels of radiation. Nuclear energy is sometimes touted as the energy of the future, but the long history of radiation exposure from atomic bomb tests and nuclear plant accidents is a cause for concern. On March 28, 1979, the 3 Mile Island power plant near Middletown, Pennsylvania, was the scene of the worst commercial nuclear accident in the United States. Radiation was released and thousands of residents were evacuated from the area. Unit 2 of the 3 Mile Island generating station shut down in 1979. Unit 1 continued providing electricity, but it was permanently shut down on September 20, 2019. The 3 Mile Island power plant is currently being decommissioned and dismantled. The Chernobyl nuclear disaster occurred on April 26, 1986 at the No. 4 reactor in the Chernobyl nuclear power plant near the city of Pripyat in the north of the Ukrainian Soviet Socialist Republic. The accident started during a safety test on the nuclear reactor, but a combination of unstable conditions and reactor design flaws caused an uncontrolled nuclear chain reaction that resulted in an open-air reactor core fire that released airborne radioactive contamination for about 9 days. By May of 1986, the radiation from Chernobyl had spread throughout much of Europe. More than 30 years after the Chernobyl disaster, milk in some parts of Ukraine still has radioactivity levels up to 5 times the official safe limit. The city of Pripyat was founded on February 4, 1970 as a community specifically designated to operate and maintain the nearby Chernobyl nuclear plant. After the disaster, the residents were evacuated and the area surrounding the Chernobyl nuclear power plant, including the city of Pripyat, have become abandoned ghost towns. Some residents have returned to nearby villages despite dangerous levels of radiation. It is estimated that the zone around the Chernobyl plant will not be habitable for up to 20,000 years. That is twice as long as our current human civilization. The Fukushima nuclear power plant accident was started by an earthquake and tsunami on March 11, 2011. When the earthquake was detected, the plant automatically shut down the power-generating fission reactors. The shutdown and other electrical grid supply problems cut off electricity supply to the reactors, and their emergency diesel generators automatically started. The generators were designed to provide electrical power to the pumps that circulated coolant through the reactor cores. However, the earthquake also generated a tsunami 14 meters high that flooded the lower parts of the reactor area and caused the failure of the emergency generators that powered the circulating pumps. The loss of reactor core cooling led to 3 nuclear meltdowns, 3 hydrogen explosions, and the release of radioactive contamination. The city of Futaba, 4 kilometers west of the Fukushima plant, was evacuated after the nuclear meltdown. Areas further away from the power station have partially recovered, and the government has declared them safe for residents. Futaba is supposed to reopen for the start of the torch relay of the Tokyo Summer Olympics after being deserted for 9 years, but the Japanese government has decided to exclude overseas spectators from attending as part of efforts to prevent the spread of the COVID-19 virus. The start of the Olympic torch relay is supposed to showcase the recovery from Fukushima's nuclear accident, but some residents think that their hometown may never return to normal. France is a nuclear power like the United States. It conducted its first nuclear test in the Sahara Desert near Algeria's border with Mauritania on February 13, 1960. This area is about 2,200 kilometers from Lyon, France, but in a strange twist of fate, windstorms from the Sahara Desert have carried radioactive dust back to France. This image shows a view of Lyon in February 2021 with a sky colored by red Saharan dust that contains cesium-137 from the French nuclear tests. The nuclear tests by multiple nations have released radioactive isotopes that make it difficult to do accurate radioisotope dating. A paper published in 2009 by Richard Firestone showed that 4 Carolina bays out of 5 had radiocarbon dates in the future, presumably from an unknown source of carbon-14 enrichment. This makes it impossible to use radiocarbon to date the emplacement of the Carolina bays. The Anthropocene is a proposed geological epoch dating from the commencement of significant human impact on Earth's geology and ecosystems. Various start dates for the Anthropocene have been proposed, but the peak in radionuclides from atomic bomb testing during the 1950s is the most conspicuous. The beginning of the Anthropocene is marked by the detonation of the first atomic bomb in 1945. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.